Okay. PoCS is a little bit in between, right? Coursework ones where it's like, oh, here's how to do something. Now do it 100 times. Very important. Really important. Wax on, wax off. Super important. But at some point you have to get into research, and that could be a bit tricky. I mean, because you've done so much course, if you're kind of in that mold of things, you need to get out there and spin the brain and suffer a little bit, actually, in a different way. Obviously, school is full of suffering, which is fine. That's how you get your brain to get to new places. But this is a bit of a different feeling. It can be very uncomfortable. Like, maybe there's no solution. Maybe this is just a terrible thing to work on. All these sorts of problems suddenly arise. So it's going to be a bit like that. So some of the projects will probably explode into flames. Education, yeah, it's a little scary. So the major themes, we have a manifesto, because I felt the need to, I just had to build that at some point. This is what complexity is, what we think about what we mean when we talk about complex systems, and what we mean when we talk about thinking about complex systems, and what a science of complex systems could do. There isn't a universal one, but there are, right, we'll come to that. But there are certainly phenomena that go across lots of systems, and the tools and the ways of thinking about them, they're very general as well. So there's some pieces here. Manifesto, which the tarot card for that one has a shovel, which is basically just get on with it, grab a shovel and get on with it. But this is basically modern science now, right? So we have this pandemic, and PoCS has got a lot to say about this pandemic. It has forever had a lot to say about it, and I am truly distraught about what's happened. I mean, many people are, of course, not everyone, but I'm distraught for many normal reasons, but also just like we know how these things do and don't work, and are deeply uncertain. We'll come to it. But it's where we need to be. So much of what we worry about in the world is post-disciplinary, right? There are systems that involve people, that involve geo aspects, that whatever it is, maybe power grids. Power grids, for example, people, the way they use things, right? And so it could be a squirrel that chomped on a wire, but it could be people using things in certain ways that make a mess of, and lead to a blackout. Whatever, traffic, the way people move around, the way organizations work, and climate change. Climate change is not just, it's obviously involves people, but it involves people not just in what we use and do, but the stories we tell about climate change, whether we believe it or not. When it comes to pandemics, again, people, of course, are we're the ones that are spreading it, right? We're the soldiers of this virus. The virus is like, thanks. Doesn't say that because it's just a virus, but if it did, and we love to anthropomorphize, it would say thanks. So yeah, we just need people we need experts, and we need people who can think a little bit outside of their boxes so they can connect with other people who are experts. But we need lots of people a good number of people who really can go across these fields. We'll talk about data, measurement, but the three corners of everything has always been data, which involves measurement, theory. Here's my model of what's happening in the real world, and experiments, right? So there's like some natural observation. I'm going to make a little experiment over here, and I have theory, and you want all those things to connect, and the really successful fields have done that, and I'll give you examples as we go through the course. Emergence, absolutely gigantic part of this, right? So, and I'll couch this in various ways, but one that I've used over many years is, right, there's no hurricane, for example, inside a water droplet. There just isn't. There's no financial collapse in a dollar bill. No love in a carbon atom. That's another one. So somehow, we put all these pieces together, and of course evolution does that for us, but physics put the earth together. chemistry put early life together, and eventually you get this emergent behavior, the behavior of which doesn't, is not present in the individual pieces. So that's, a profound thing. Actually originally came out of philosophy. We'll come back to it. And then there's this tension between universality and accidents of history, right? So the platypus is a platypus, pretty weird thing. But say, it has, if we look at, say, fish, swimming in a fluid, you're not going to have fish that are shaped like, I don't know. I mean, there are some pretty weird shaped fish, it's true, but and the ones that are, they're not going to be things that cannot move in the water fast if they're trying to be fish, right? That's just not a good plan. So they tend to be what we think of as fish shaped. We have rays. That's a 2D thing, sure. But they're going to respond to fluids, and fluids have a universal story for them. Navier-Stokes equations, right? So if you had fluids on another planet, the things that swim around in it would be kind of in the same game plan. Same with plants, phyllotaxis, the way things grow, there are sort of limits to the kinds of shapes that get produced. But yeah, there's of course then accidents of history, and we can end up with we get locked into things, right? We build out a DNA. We're not going to evolve a new story for that at that level. So, yeah. Anyway, so we'll get to some of that. But yeah, so we want to understand how things become things. It's basic science. And, a really profound part of that is this micro to macro mechanism story. Not everything works in that way. It's not just like everything just combining in a nice way. Some have feedbacks from the outer loops and so on and so on. But this is a really sort of just, we've got to get this right. There's going to be scaling. There's a big part to start with. It's just a really, really profound part of thinking about systems. What I'll call statistics of surprise, which again is a scaling piece, which is kind of various examples, but earthquakes perhaps, right? So lots of tiny little tremors. Now and then there's a bigger one. Every year there'll be one of a certain size, pretty variable. Every 10 years, every 100 years, every 1,000 years. So it's a logarithmic story, and we'll kind of harden that up. Floods are another example like that. Things change over time in problematic ways. Such we say, the 100-year flood comes every year, but that's a way of encoding this, this unexpectedness. But statistics of surprise. And eventually we'll show that pandemics are kind of the worst, actually, the most deeply unpredictable, at least to my knowledge, of what I'll call natural disasters. Networks, enormous part of thinking about complex systems. Many systems have a network structure, not all of them, but at all, but that's a big part. Robustness is a big piece, like why do things stay together and not fall apart? And it's been a challenge to understand that theoretically. Ecosystems, we worry about them falling apart all the time, but of course they are there, so there's a lot of day-to-day stability in systems, a lot of day-to-day stability in societies, but they can fall apart rapidly and explosively, and we'll touch on ways in which that can be seen as happening through models, of course with real-world examples. But let me just add a piece here about the structure and stories part. Is we will come to this, I think, hopefully repeatedly, where the mechanisms and stories we come up with, often they can be toy models. What we'll talk about is toy models, which are really simple models. Right, we'll talk about the icing model, for example, for magnets. There's models for how people copy each other and so on. They're really simple, right? There's no complex kind of humans involved. They do one thing, they copy or they don't copy, whether one tiny little aspect of behavior, and we put them in some network. So what those kinds of models can tell us is how collectives behave, and the sort of possible modes of behavior. And that is incredibly important, because we are, and this is a deep thing, I think, we are very good at seeing how individuals might behave, because we're individuals, we can kind of track them. and we try to reduce systems to individuals all the time. So it's a great failing. We're not good, and the linear algebra thing here is left null space contains the stories of collectives. We're just not good at seeing them. We're not good at seeing them. We're not good with probability as well. It's another thing we'll talk about, but we're also just not good at, it's just not a natural thing for us. We like to impose a story of an individual on top. So simple models do that for us. Complex models, where we put everything in the kitchen soup, we're trying to absolutely replicate, you know, the traffic of this place, or the, you know, how people are spending their money, you know, like really detailed kind of model of it, or a really detailed model of the fault system in California, or the, you know, the climate. That's where we're trying to put everything in. We're trying to make our little computer version of it and run it forward. So it's kind of hard to be in between those places in a useful way, and I will return to that. But so I just want to sort of say this, that simple models have this real place in the world, and because of the stories they tell us. But there's a limit. There's a limit to them. Okay, theory of anything. We're not going to do it. But why complexify? You know, why is there this ratchet of complexity? I mean, I think I've touched on a few of the pieces that are there, and why we should kind of expect to see it, you know, this ratchet take place in over and over. We ran the universe again. Of course, we're not aware of life somewhere else, but we also know that things can get capped at different points, right? That life won't work out. All right, it's all about stories.